I believe we are live.
Oh boy,
Can you hear me now?
I can hear you. Can you hear me?
Yeah. Hello, lemon heads. And what do you call your guys?
We're not that cool. We don't.
No?
We don't have names.
All right, we're going to try not to make this video too long. Mr. Dealman and I had this great idea that we would come to you together and try to create a video for the next little bit of our story on sine and cosine. And it gets a little sticky, so we thought two heads are
Better than one.
better than one. And so we're going to try something here tonight. It is tonight, and we're going to talk about some trig functions called sine and cosine graphs. We've been looking at a circle, and we're going to, see how this goes. I think we're ready for the Ferris wheel, Mr. Dealman.
I sure hope so.
Okay, I'm going to try this. Screen, share, double click on this. Are you there?
Yeah,
Can you see the Ferris wheel?
I sure can.
Boys and
It
girls,
is
can you see the
spinning
Ferris wheel?
round
Spent
and
a
round.
lot of time creating this. It's actually a pretty good production. You're going to be, I thought I turned that off. Yeah.
One more.
We're going to start the Ferris wheel right at the, I call that the 3 o'clock position or 0. Mr. Dealman, how many radians are there in 360 degrees?
2 pi radians.
Yeah, so I'm going to write that down. 2, I don't like that color. Red, actually, you want to capture somebody's attention, write it in red. 2 pi is equal to 360 degrees. We should know that by now.
Mm-hmm.
You know that because, well, I can't say why. 2 pi is equal to 360 degrees. Probably 1 pi is then how much?
180 degrees.
That's what I would guess too. And then probably pi over 2 would be something.
90 degrees.
Uh-huh.
Follow the pattern.
Except now I screwed up the pattern.
Well,
So
there's in between the 180 and the 360.
there's going to be a 1.5 pi or 3 pi halves. How much would that be?
270.
270. So those are pretty good anchor points when we're
Mm-hmm.
thinking about, we're going to try to teach you or remind you, hopefully not teach you, remind you of the sine graph. One of the videos that we assigned did show this, but we're going to show it to you again. So this is like a angle axis, which we could call theta, and that's the angle measure, and this is still called the y-axis.
Mm-hmm.
And how much you think this should be?
Well, if that's our end point, we always refer to one full revolution as. Want to start with degrees?
Sure.
Stick a little familiar. So that'll be 360.
And then I'm going
That's
to go
our
halfway in between the beginning and the end, which would then be,
180,
and then halfway between 0 and 180 would be something.
90.
And then between 180 and 360 is always something.
270.
That's what I would have guessed as well. All right, so guys, uno, dos, 3, 4, 5. Okay, there's 5 points. That's really all you need to graph this equation. This is what we're graphing. I don't know why I have it way up there because I typed it a long time ago, and but that's what we're going to graph. Now, if you remember, the sine is the distance you are away from the x-axis. All these represent a height from this axis. And as we start rotating this Ferris wheel, you are at 0. And then you obviously rise a little bit higher, still a little bit higher, still a little bit higher, till the maximum. Well, let's start here. That, I believe, would be this point on the graph. My height is 0 at 0. It's going to take a little back and forthness here. Rotate. I'm going to stop 1/4 of the way through my rotation.
Which would be 90 degrees.
Okay.
Which is one of those anchor points like you pointed out.
And what would be the height then?
Well, what's the radius of this circle?
I don't know. Did we determine a radius of the circle?
I think just to assume, which I don't need to explain what assuming does to us, but it is going to be typically the unit circle, so just 1.
Okay.
Radius 1.
So we're going to say a radius of 1. So that means at 90 degrees, a quarter around the circle, I'm at a height, the Ferris wheel dude, is at a height of 1, whatever the unit is.
Yep.
We'll continue our journey. It's pretty fun, isn't it? Hang on, because you're about to go upside down and lose your cookies.
Which, I was thinking about that earlier. You mentioned that joke earlier when we were running through this, and I was like, what Ferris wheels do you have the swivel on the cart, and so you never actually go upside down?
Way to wreck my joke. All right. What would that degree be at?
Well, it looks like you're back at ground level.
So
you'd have a height of 0. So
I'd be at a height of 0. So I'm halfway around the circle, 180 degrees, a height of 0. We'll continue on to the next little stopping point, which is going to be the bottom of the circle, or 270 degrees. What would be my height at that particular stop?
This is our minimum most point, so that'll be a -1 below.
-1 below. And then we go back to one more, come on, complete the circle. We go one more quarter of the circle, and lo and behold, we're back where we started. So we're back here. So sine, ladies and gentlemen, looks something like that. It's not perfect, but it's close.
Mm-hmm.
Okay?
It's better than connecting the dots with a straight line.
That's correct. It is a fluid flow thing. And then, guys, it starts to then, and I ran out of room here, but it's going to repeat this S. There's no good way to call this. I call it a sideways S deal when you got a better way to think about it. I know a sideways S is a big stretch, but what else the heck do you call it?
I don't know. I've never really had a name for it.
Okay. Well, it looks like that. How's that sound? You call it what you want. Make up your own name. Now, if we go to radians, I don't need to go through it all again, do I? I think I can just do this. Get out the eraser and get rid of that dude, get rid of that dude, get rid of that one, and get rid of that one. And just to make an emphasis, we can even change colors now. Back to blue.
Fancy.
So now, if we think about one full revolution was 360, that's 2 pi.
Yep.
If that's 2 pi, this must be pi.
That's halfway.
That's halfway. And then this would have to be
half a halfway, so pi over 2.
Pi over 2, and then this would have to be the 3 pi halves. If you look at this circle, it would be 0. This would be pi halves. This would be pi. This would be 3 pi halves. And then this is back to 2 pi. If we did it in degrees, we go to red, we'd say 0, 90, 180, 270, and then back to 360.
Yep.
You have to remember the sine is the vertical distance you are away from the x-axis.
Mm-hmm.
Think we're ready for cosine?
I hope so. I hope they remember that cosine represents the x value of your point on your Ferris wheel. And so we're going to have to think of the graphing of our cosine function the same way as how we graphed our sine function, but instead of focusing on how high we are or how far above the x-axis we are, we're going to figure out how far away from the y-axis are we with the cosine of x. Now it's a little bit confusing because we've got y equals sine of x and y equals cosine of x, so you have to keep that separated in your mind. But if you remember, one, cosine gives you your x coordinate, your x value, and sine gives you your y value on your circle. Keep that straight. Don't forget about where we're coming from. But then once you put it onto a graph like we're about to do, you kind of have your independent variable as theta and your dependent variable as y.
Okay, so let me get this eraser out. We're going to get rid of these dudes.
Yep.
I'm afraid this is taking way too stinking long. Sorry. All right. So as he said, now we're measuring the distance from here to here. So the radius is going to be 1 again.
Mm-hmm.
So this time, if we're graphing cosine, and that's way too far to the left, but anyway.
I can see it.
You can see it. All right. So I'm going to be 1 unit away. So cosine, as Mr. Dillon said, measures the distance I am away from the y-axis. So I'm at 1. As we start to rotate up, I'm going to get closer and closer to the y-axis.
Mm-hmm.
Let's rotate that baby. We'll make our first pit stop at 90. Oh, wait a minute, dude. We
I need
need
the
one of
label.
these. What do you want? Degrees again?
Sure.
360. Look how fast I'm getting. 180, and then 90, and then
270.
270. Thank you. 270. So start out at 1. I'm at 0. I'm at 1. Then we're going to rotate. Let's rotate. Make a first pit stop at 90 degrees. How far am I away from the y-axis?
Not at all.
I'm on it.
Yep.
So the distance I am away, I'm at a 0. So my angle's 90 degrees, and the distance is a horizontal distance. We're perfect. We keep rotating. We make our next stop. Oops, I just wrecked the Ferris wheel. Oops. We're going to go to 180, and then that would be something. How much high would that be?
Well, this is where you got to kind of think, okay, well, I'm actually in negative land in terms of my x value, so
Good
I'm
thinking.
-1
Okay.
below.
So I got to go down to -1.
Yeah.
Yeah.
And some
If
of you
this
might
is
be
1,
seeing,
0, yeah.
you might be noticing the pattern already is kind of the same as sine. You can probably guess where the next point's going to be.
Yeah. If we could hear your voices, we'd take bids, or I don't know. Rotate again, and then we're at something. Back to
on it again.
0, so we're on it. We're not anywhere ways, and then we rotate one more time to 300. Dog bite it.
You'd think you learn.
Yeah, I'm not. That's not even. I can't even blame it on too much coffee because it's nighttime. Then that would be back to 1.
Back to 1.
And this baby then. Now that I promise you looks like a V. Is that what you would say?
I'd say so.
So a V-shaped figure for cosine, and then again, dude, guys and gals, it's going to go V once, V twice, V 3 times, and every time it's going to happen, this V shape is going to get repeated every 360 degrees. Yeah?
Yep.
And then, I don't know, do I need to bore you with the pies? Change back to blue. We could just say that this is 2 pi, half of the way is pi, and then half of pi is pi halves. Same thing we have written up here. And then this would be 3 pi halves. So if you're in radians or degrees, the graph is going to look the same. It's just a different unit on the x-axis. Different angle measure, because we can measure angles in both degrees and fill in the blank. You paying attention or not?
I am. I just wanted to see what reaction you'd give.
Well, say it then.
Radian.
Okay, good. I thought you weren't paying attention. Degrees or radians. And you should be able to convert back and forth because we probably showed you a few videos on that as well. Mr. Dealman, are we ready to transition to something different?
I'd say so.
Okay, so just one final thing. Dudes and gals, you need to know how to graph those because now we're going to start messing with these things. Yeah. And if we don't have a foundation on which to build, we're going to be in trouble. So anybody have any questions? What questions do you have is a better one. You got any on your end?
It's pretty quiet.
Pretty
but
quiet.
Actually, though, if you do have questions, you can go on the Google Doc.
Yeah, we're there from 8 to 9:30 and from 11:30 to 1 every day. We'll see you there.
So, if there aren't any questions, what do we do if this... So right now we're in a unit circle with radius 1.
Yeah.
Realistically, no Ferris wheel is going to have a radius of 1 centimeter, meter, foot. That's not an accurate. So what if it was like a radius of 5 or something? Maybe it's a miniature Ferris wheel. But what if the radius is 5? What happens to our... Well, not only the Ferris wheel, the wheel's going to be bigger, but how does that translate to the graphing of the sine and cosine curve?
So we're ready for something else. Is that what you're telling me?
Yeah.
Okay, so I am going to, what do I got to do again? New share. And then I got to go to, come on. Did I do it?
Yep.
But now guess what? I only see you.
That's not okay. You need to be sharing.
Okay. I don't know what happened, but I had to go back to those 2 dots again.
You're good now?
Yeah.
Okay.
Neither one of us wanted to be the Lone Ranger on the video, so we worked really hard at making sure that wasn't going to happen. That wasn't so bad. I could have just left you up there.
I was just going to say, I'm glad you spoke up. All right.
That was dumb of me. All right, back to the drawing board. Sine X. This is a weird looking sign because I could have sworn you said it was kind of going up first and then down, but there's a reason why that is.
Yeah.
Guys, if you look over here to the left, we have a couple of functions. There's a letter A in there, a letter B, and a letter C. Those are called parameters. Parameters. P-A, I won't spell it. Parameters. Those things change the graph. And I'm just going to play. This is what's fun about technology. I can slide to the right. I can slide to the left. But we can't crisscross. Slide to the right, slide to the left, slide to the right. No crisscross. You can't. All right, that's all we got. Slide left, slide right, slide left, slide right. Notice, please, I'm so easily entertained. I could do this all night. There's something about it to me that's just kind of fun.
Hit the play button. See what happens.
Oh yeah, we could just
Oh.
don't have to even touch anything. It just kind of does its thing.
Oscillating.
And we're gonna have to talk about A, what effect that has on graph. You probably already know. B. Yikes.
That's not today. We'll talk about that tomorrow or.
Yeah, we're hoping that tomorrow we'll be talking about letter B. We'll probably come back at you live again, only via recording, which I guess isn't live. And then letter C, that's probably in my mind, I ain't the sharpest knife in the drawer, but that to me is the easiest one because it looks like you grab onto the sucker and you go up and you go down. That's the fun though. You slide to the right, wow, it goes up. That's confusing. Slide to the left, it goes down. Still no crisscross.
Correct.
All right, so let's see if we can't reproduce y equals sine x. In order to be y equals sine x, c would have to be 0. B is going to have to be 1.
Ooh, there you go.
We're going to leave b at 1 because that's a different video. And then a would have to be
back at 1 as well.
Back at 1 as well. So we said we started out on the Ferris wheel at height 0. We went up to 1, back down to 0, down to -1, back to 0. 2 pi. Now notice, please, this is in radians, so it's a little over 6. 2 pi is 6.28. So you can see the period. Maybe you should tell them about that word, Mr. Dielman, period.
It's pretty much how long, and now again, when I say like how long, well, what measurements are we using? We're measuring in this case, radians, but also degrees. So how long does it take to go 1 full revolution? Now, with the sine curve, you got to go up to your max point, you got to go down to your minimum point, and you got to go back to the start at a height of 0. So how long does it take us to go from 0, 0 to get back to go up, down, and then back at it 0 again? And that takes about 2 pi radians.
2 pi
exactly
radians.
2 pi radians. And so that is the standard form of sine of x. And so that will be the case for, that will be the period for sine of x and for cosine of x for that matter, in that standard form.
Okay. And if you look over here, I'm going to call it the sideways S because I don't know what else the heck else to call it. Here's that same, I start at 0, go to the max, as you said, back to 0 to the min. So here's another repeat of it as we move into negative land. And it's called a periodic function because it has a period and it just goes, it's like straight from the Department of
Redundancy.
Straight from the Department of Redundancy Department. It just continues to, go. You can do this with your hand. It's really fun. If you ever go down 60 miles an hour, stick your hand out the window, you can make the sine curve really nice. Yeah. All right. Now what? I guess we better talk about A, or do you want to say something important?
What effect does A have on
there we go.
Sine function?
So we had talked to Mr. Dielman and said, what if the radius of our Ferris wheel wasn't 1? Well, look what happens to graph if we make it 2. I can't make that go slow motion, so just kind of look at it. Something changed. Students? Anyone? Ferris? Anyone?
Bueller.
Yeah, I think when I'm watching this, Mr. Dillon, what are you seeing changing?
It looks like it's getting. It almost looks like if you were to grab the maximum point and the minimum point and pull them in opposite directions, that's kind of like we're stretching it out.
I like that. I
We're
like
not
that.
changing the period at all.
I
Okay.
like that. The stretching it out. And then I can keep going and we can keep stretching. And if we go all the way to the end, we could, because this has a maximum of 5.
Mm-hmm.
What I love about Desmos, if you click on this, you can go right up here and you can see that that maximum, come on.
I think you can actually click on the point.
Oh no, now what did I do?
Oh.
Click on the point. Hey, pi halves 5. That's pretty exciting. I just spit all over my computer. I got so
You tell our
excited.
math teachers when we get excited about seeing.
Uh-oh.
Oh no.
I know. What did I do?
I think. Oh no.
Dude,
Hit the.
I can't hit the below this button. This one? Zoom
Yeah.
in, zoom out, and shake it all about. Do the hokey pokey and turn yourself around.
Yeah, we'll be all right. I can see it.
Uh-oh. What are you seeing right now?
Well, I don't see the sign of the cosines on the
Okay, well,
side.
I see the Ferris wheel picture that we just saw, so I'm a little
No.
bit nervous what to do here.
Just go back
How about a
to.
new share? Go back to this one. Uh-oh.
I think you're already on it. So try hitting Command Tab to try to switch
I'm
back
good.
into
I
Safari.
see it now. Oh, doggone it.
There you go.
All right, I'm good. Are you guys seeing it? I guess I can only listen to you. Are you seeing it?
Yes, we're good. Full
All right.
screen now. We're good.
Okay, so we're beating the dead horse dead here. Guys, all the A does is change the maximum minimum points. I want you to stare at the 0. And notice, please, that's not changing. Stare at pi halves. Notice the x-intercepts are not changing. The only thing that are changing, as was stated, the max and the mins. I liked his verbiage of stretching. Now, technically, Mr. Dillon, we have negatives on here, but we don't really want to talk about negatives tonight, do we? Because that's going to be a reflection across the x-axis, and they don't in today's lesson plan.
We're not really talking about that.
All right, we're not going past that. That's interesting. It makes a straight line. Can anybody tell me why when A is 0, it's a straight line?
Anybody?
I got nothing.
I guess it's just me.
Yeah.
Anything multiplied by 0 is 0.
Yeah. So this whole expression here is 0, and of course, f of x equals 0 is a straight line through 0. Math just makes sense. It's just incredible. All right. Well, you better talk about the word amplitude, maybe.
I was just going to say, before we move on, amplitude. Yeah. I always, whenever I hear that word amplitude, my mind always thinks to, like, sound waves. And I don't know if that's an accurate way or an accurate connection, but in this case, we do kind of have waves with this sine function. And we've got a peak wave, and we've got I guess you could say in economics terms, a trough wave, right? So we got a high point and a low point. And the amplitude is really just the height from the x-axis to the peak, or the x-axis to the trough, right? The max or the minimum point.
Can you see this cursor going bouncing up and down or not?
Yeah, I can.
So you said from the maximum to the x-axis.
Guess you could say the height of the peaks.
The height of the peaks. And then this would be a height of 1 as well, but technically it's height of -1, but we don't think of heights as being negative, I guess, right?
Right. And actually it would be 3, because we've got a equals 3 right now.
Oh, yeah. Good thinking. I thought I was on 1. Now I'm on 1.
Hit the plus, zoom in a minute so we can see. Oh, that's weird.
Yeah, I don't know.
Can you not hit the plus on the sidebar?
No, because the pictures are in the way. I got to do this all the time.
Drag them out of the way then.
Yeah, you young punks think everything's so easy. Oh, that was pretty easy.
It was.
Now I don't still see them.
I don't know.
I don't know either. Let's just use a bigger amplitude. Let's just make it. Oh no! Now I changed my whole scale.
Yeah, that's what I'm talking about. I wish I could have my mouse jump in there
and fix it.
Yeah, but I can't.
Well,
oh, there we go. Hit plus. One more, and then change the view. There we go.
I don't know why that plus and minus just came back. Do you?
I have no clue.
Good. Maybe you can.
Anyways,
Anyway, go ahead. What were you going to say?
The amplitude, yeah, that's something that you're going to see come up in homework problems. If we were to give you a quiz, or you'd see it if we give you a review sheet, we're going to give you a question. It'll be calculate the amplitude, or the situation with the Ferris wheel, they're going to say calculate the amplitude of the sine curve or the cosine curve for the Ferris wheel's coordinates, right? Mapping out the coordinates using sine and cosine. And so when you got to calculate an amplitude, what we're looking for is a positive number. Am I right, Mr. Lemon?
You are.
For a positive number.
Okay. Something just happened.
Well, sometimes bubble.
Got a carpet video?
I don't know what. I'm not lying. I don't have a clue. The ghost took over this machine. Now look at all of our graphs are gone.
Oh no.
Oh.
Well, we're too far in to turn back, so.
Oh my gosh. We are going to talk about B anyway, so plus C. We got to end this. That's scary.
Oh, there you go. So yeah, basically when you're C is 1. That's why it's sitting up. But
well, maybe we should transition to that.
Put it back to 0. So yeah, when we amplitude, right? It's pretty much just the height of the peak, right? So what's the positive distance, or I guess you could say what's the absolute value of the difference between the maximum point to the x-axis or the minimum point to the x-axis? Obviously, you need to change, right, from the x-axis to the minimum is going to be a negative number. But we really only describe the amplitude in positive land. So in this case, since A is 4, our amplitude is going to be 4.
Yeah, it's pretty straightforward. Whatever number A is, that's going to be your amplitude. That's another way of thinking about it. And some books will explain it as the maximum minus the minimum divided by 2. So 4 minus a minus 4, which is 8. 8 divided by 2 is 4. If you made it another number like 5, I'm not trying to insult your intelligence, but 5 minus a minus 5 is 10, divided by 2 is 5. Yep. Amplitude, we beat that dead horse dead. All right, let's talk about C real fast. We said that was pretty easy.
Yeah, you can kind of see.
All that does, guys, is grab onto it and raise and lower it.
It's got a similar effect to the C term for a quadratic in standard form,
yes.
But the key difference is it's not the y-intercept. So don't be confused and say, oh, the y-intercept is going to be 0, c. Nope. This is definitely different. It's a different family of a function. It's going to, especially now that we've got the amplitude and this constant term C, and then tomorrow we'll introduce a parameter B, it's changing it all quite a bit. So,
so
yeah,
guys,
it's got the same effect.
That's it. That's all we need to know today. We're trying to get at what A does and what C does. And of course, we needed to know what sine x cosine x was before we added these two parameters. So, I guess, you think that's a wrap?
That's all she wrote. I mean, we babbled a lot, and we went to see a carpet video, so I think they've gotten a lot of extracurricular activity here, so I think we're good.
Yeah, okay. I'm going to say stop share.
Oh, back to
so now I can see my buttons up here. So are you ready to sign off?
I'm good.
Okay, guys, you'll see this tomorrow morning. I hope it works. See ya, Mr. Dealman.
Adios, Mr. Lemon.